students. Now, from today onwards, we are going to learn a new topic in physics, that is solid state physics. So, before going into that, let me tell about another topic which you may be familiar with. You might have heard about it, that is condensed matter physics. Okay, basically, this is a larger area in physics which comprises the study of or the microscopic and macroscopic study of the properties of solids and liquids. Okay, so condensed matter physics deals with the study of physical properties of matter, which include solid as well as liquid phases. So basically, we study the forces acting within the atoms and molecules in the solids and liquid phases. Okay, so this study basically include this condensed phases. When we say these basically include superconducting phase or magnetic, that is ferromagnetic and antiferromagnetic phases, and all the Bose-Einstein condensate. You might have heard all these. So you'll be learning more and more about these topics in this year. Okay, so this is about the condensed matter, and this is a very promising field in physics because like all the researches in material science, or this can be basically material science is a topic which comes under this condensed matter physics. Okay, and nanotechnology, and these are all very important on various topics such as crystallography, metallurgy, magnetism. All these comes under basically this condensed matter area. And then superconductivity is another important topic which comes under this category. Okay. Now, when you say condensed matter physics, it is a larger top area which comprises both solids and liquid phases. But now when you talk about solid state physics, okay, so this basically comprises the study of the phase solid. So solid state physics is the study of the solids, which okay, solids means all the solid matter. And then this is also very important because it is an emerging field. So quite a lot of research is done in this particular area, but then lot of research is still going on in this particular area, even in superconductivity or in ultra-cold phase, Bose-Einstein condensate, or even the semiconductor technology which we are talking about, like all the semiconductor stuff like diodes, transistors, all these are basically solid state materials, or solid state electronics we call them, electronic materials. So all these are still further research are going on this particular area. So this fundamental physics which we are talking about in this solid state physics, this stands as the base for the research topics which comes under this solid state materials. So this is quite important, this topic. Okay, so we shall now start learning different topics in this particular area in physics. So here today we are going to understand about the dielectrics. Okay, so we shall see what dielectric is and all these things. I've shown here the band diagram, energy band diagram of three types of materials. They are metal, semiconductor and insulator. This you might have already studied, you know this. So we have learned that in actually the energy, when you think about the energy band diagram, we can think about two bands. One is the valence band, other one is the conduction band. And you know that in metals, there are a lot of free electrons in the conduction band, right? So we say that there is no energy difference between this valence band and conduction band. That means the metals are very loosely packed, or they can freely move inside a metal, which means that there is no energy barrier between this valence band and conduction band. Or in other words, we say that the electrons are free to move. Free to move when we say that, it means that there is no energy gap between this valence band and conduction band, and they are almost overlapping. So that is what is shown here. Okay, but when we come to semiconductors, you have studied when you started learning about this semiconductor, p-type material, n-type material and all. So there, for semiconductors, there also exists valence band and conduction band, but there is a small energy difference between this valence and conduction band. So we can say because of that small energy band, we can say that the conduction band is almost empty. Okay, so which means that the electrons from the, if it has to get over this energy band, and then if it has to jump from the valence band to conduction band, then they require some energy. So in the basically in the temperature, or when the temperature slightly increases, this valence electrons in the valence band can actually overcome this energy difference and come to the conduction band. So and there is a difference between the valence band conduction band energy difference, but still the difference is small. So if you give a small energy, the electrons can jump from the, or it can start conducting. That is what you mean. They jump from the valence band to conduction band. It means that electron can start conducting if a sufficient amount of energy is given. But now when you come to the insulators, they are basically a still more a different category, which means that insulators, we know that there is no conduction. No electrons are free to move, or which means that such type of materials never conduct electricity. Okay, so when such type of materials, when they doesn't conduct electricity, according to the band diagram, what we can say is there is a lot of difference, a large difference between the valence band and conduction band. So that means normally the electrons will not get that much sufficient energy to actually get transferred to the conduction band, or you can say that the no electrons will basically help in conduction in the case of an insulator. So these are actually categorizing materials or solids on the basis of their conducting electrical conductivity. Okay, so this you already know that I have explained. Now you might have understood what's happening here. Now basically this insulator category can also be called as, or you can say that this category of solids can be called in another name, and they are called as dielectrics. Okay, so that is what a dielectric is. So they are materials where the electrons in the material will not directly take part in electrical conduction, or they will never basically help in the conductivity of the material, which means that the material doesn't conduct electricity. Okay, but then and because of the difference between the valence band and conduction band. But when you say dielectric is a special category of insulators, or you can say that all the dielectric materials are insulators. But then I cannot term every insulator as a dielectric. Okay, so I can say all dielectrics, they are insulators. All dielectors, they are basically insulators. Their behavior is like this. Okay, but then, so which means that dielectrics are a special category which comes under insulators, but they have a special behavior. That means they actually doesn't help in conductivity, or which means that the electrons are not free to move as such in the case of a semiconductor or in a metal. In dielectrics, electrons are not free to move. They cannot move on their own. So we call them as insulators only, but they have some peculiar nature, or when you give an electric field to those materials, they behave in a different manner. Okay, and that is why they are called, though they are insulators, these materials are called or given a special name called as dielectrics. So what a dielectric means that they are a category of insulators, okay, which but behave in a different way when an electric field is applied to. Basically, it doesn't give rise to conduction, but then it has a peculiar property. And what is that property? We shall see now. I have shown here an atom. Okay, you first see this particular figure. You have an atom where you have the positive nucleus inside, and the electrons are distributed around the nucleus. They are orbiting in different orbits. Okay, so you consider a molecule such that its positive center, there is an electron cloud here. So where is the actually center of this electron cloud? I can say since it is distributed all around, the center of this electron cloud can be put here itself. So the center of this electron cloud I can consider here. Okay, and the positive core, the nucleus is always within the center of the of the atom. So the negative and the positive centers, they are coinciding here. Okay, this is a particular type of atom where the its negative center as well as its positive center is coinciding or overlapping. Okay, now suppose if I give a small electric field to the atom. So let me say that I give an electric field to the atom. So this is basically an not we will be applying the whole thing to a dielectric material as such. We don't get an atom, an individual atom. We don't get at hand, right? But then this is for you to understand. So if I give a positive charge here of over the sphere, if I give a positive charge here and a negative charge here, what happens? What happens is that sorry, let me give as per the figure, let me give an opposite polarity. So this is say negative charge and say here I give a positive charge. So what happens? You can say that the center of the electron is here or electron cloud is here and the nucleus is over here. But because I gave an electric field because I gave an electric field here, they see because of the negative charge, what happens? The positive core will slightly move towards this, right? And the negative center will slightly move towards here, which means that the nucleus will get shifted slightly towards this because since I applied a negative charge here, okay, and positive charge here, the electrons slightly will shift towards this positive side. Okay, so based upon the electric field which I apply, since I have given a negative here, this positive center slightly move towards here, and since I have given a positive here to this part of the sphere, then the negative electrons slightly shift towards here. Okay, so now you see individually in the atom there is a slight localized, we say a localized, actually localized production of positive and negative separation. Okay, and this type of materials, if in a dielectric, so if it happens in an atom and this atom actually is comprised or a dielectric material is comprised of such atoms or okay, so then basically that dielectric material will have localized charge separation and we can call such materials as dielectrics. Okay, but then so insulators which show this type of a behavior, that is a charge separation when an electric field is applied, we can call the insulators as dielectrics. And there are insulators which doesn't show this behavior. They are generally never called as dielectrics. They are called as insulators only. Okay, so this is about this a slight discussion of what is basically happening within a dielectric material. Okay, now I'll show you a dielectric material. Now, before going into the further details of dielectric materials, we shall understand what polar and non-polar molecules are. Okay, here we have shown two sets of molecules. So you know that all these are formed by covalent bonds, hydrogen chloride. Okay, so that is HCl, they are actually covalently bonded. But in this type of molecules, there is a peculiarity that one of the electron will be more electronegative. Okay, so that means the electrons will be, though they are shared between these two, the electrons will be more actually attached to the chlorine atom here. Similarly, this is the case of a water molecule, and here also we can say that it is a bent structure, and here we share the oxygen, it share one of its electron with the hydrogen. Here also such it is covalently bonded, but then because of the electronegativity of the electrons, the electron cloud will be more attached to the oxygen, and similarly the positive core will be more towards this hydrogen. So if you say the centers of this the positive center and the negative center will be slightly shifted with the difference, which means that just before I was telling you that in certain molecules the positive and the negative center will be coinciding, right? It is not that case here. Already, even if you don't apply an electric field, The positive center and the negative center are already separated. And because of the slight electronegative behavior of one of the atom comprising the covalent bond, there is a basically a charge separation within the molecule even if you don't apply an electric field. Similar this is the case with the NH3 molecule as well. Okay. Now you consider there are certain molecules like nitrogen molecule. Here they are covalently bonded, but none of the because both of them have the same behavior. Here the positive and the negative center will be coinciding in this molecule as a whole if we take. Here also we can say that CO2, the oxygen though has a slight electronegativity, but then negative will be shifted towards the left. Similarly here also the negative center will be slightly shifted towards the right, but then both of them are symmetrically oriented towards the left and the right, that will cancel out. So which means that there is no basically charge separation in the CO2 molecule. And similar as the case of CCl3 molecule itself. Okay, so there are certain molecules, category of molecules, where if you don't apply an electric field, there is no charge separation as such within the molecule. Okay, but there are other certain category of molecules where even if you don't apply an electric field, there will be a charge separation within the molecule. And this type of molecules are called polar molecules, and these are called non-polar molecules. So this is a behavior of a molecule on its own without any application of electric field. So this is very important because when you talk about dielectric materials, this type of polar and non-polar bonds or polar and non-polar molecules can come within the dielectric. So now whether it is polar or non-polar, in a dielectric material, if you apply an electric field, here you can say non-polar, already there was the positive and the negative, or no, the positive and negative centers are coinciding, but when you apply an electric field, this positive and negative center will separate. Okay, charge separation take place. Here also all these molecules, even so that is when without applying electric field, there was no charge separation, but when you apply electric field, charge separation take place in the case of a non-polar dielectric material. Okay, now in the case of a polar material, already without any application of electric field, charge separation was there. So now when you apply an electric field, basically the charge separation will become more intense, right? The charge separation already exists, so that becomes more intense, and that is the case of a polar dielectric material. Okay, now you see here I have shown a dielectric material. Okay, so you don't bother about this electric field and all, but then just see this. Here there is a dielectric material. Okay, and next to the dielectric material a metal conductor is kept. Okay, now what I do is I give an electric field to the metal conductor. Okay, so let me give a positive and this is given a negative. So there is a potential is applied across this. Now what happens whether it is polar molecule or a non-polar molecule, whatever it be. So if it is non-polar, the centers were first coinciding, this positive and negative centers were first coinciding. If it is non-polar, sorry, if it is polar, the centers were not coinciding. If it is non-polar, the centers were already, or initially it was coinciding, but whatever it be, now I apply an electric field. So if I give a positive here, what happens within each atom or within each molecule, a charge separation takes place, right? Since I've applied a negative charge here within each molecule, a negative, sorry, since I have applied a positive charge here, within the molecule, this negative center will slightly shift towards the left. So at every individual molecule level, the negative center will slightly towards the left because of the positive charge applied here. Similarly, all the positive centers in each atom will slightly get shifted towards the right because of the negative charge applied to this face. Now you see, so all at local level means at each individual atom or at an individual atomic or molecular level, we can see there is charge separation, right? But then you can see this individual charges will get cancelled because here positive here a negative. So this will get cancelled, right? Here there is a positive, there is a negative, this may get cancelled. Positive, negative, cancel, positive, negative, cancel. Here also positive, negative, cancel, cancel. So within the material, actually all this positive and negative will get charge will get nullified. But then at the end, so within the material this will get cut off or it will get neutralized, but then towards the end of the dielectric material, all the negative charges alone will be standing. Here also all the positive charges alone will be standing towards the right. Okay, so here negative charges are gathered together because of the positive charge here. All the positive charges are gathered together because of the negative charge given here. So we can say that there is basically net resultant charge separation which takes place at the surface of the dielectric, and we call these charges as bound charges. Okay, we call this as bound charges in dielectric materials. Okay. So this is about the main thing happening or main physics happening in the dielectric material. And now we call it, you have studied about electric dipoles. So this charge separation, an individual charge is separated. That is, now I can say that all the plus, or if I say individually, the charge of this one is say Q. Okay, and the distance between this negative and this positive, or that distance between this dielectric material or the thickness of the dielectric material, let it be R. Okay, so then I can say that the dipole moment P is denoted by Q, one of the charge into the distance, perpendicular distance between them. Okay, here you have two charges and the perpendicular distance between them is R, and one of the charge, positive or negative. So here one of the charge. So dipole moment is basically one of the charge multiplied by the distance between the two charges. So what is dipole? Dipole is a positive and a negative charge separated by a distance. Okay, and that is dipole that you have to learn. What is a dipole? Okay, and what is a dipole moment means one of the charge multiplied by the distance between them, and that is called as the dipole moment. Okay. Now the total dipole moment is what? If suppose if you have n such charges, okay, and n such charges separated, each of them separated at a particular say Ri, okay, then I can say the total dipole moment P is equal to sigma, okay, Qi Ri. Okay, so similarly you have to sum for I equal to 1 to n. So if there are n number of charges, you can say that the total dipole moment is sigma I Ai Ri. Okay, so that is about the total dipole moment. Then another important parameter which always discussed is polarization. So basically we know what dipole moment is. So dipole moment is actually the total dipole moment is the sum of all the dipole moments of the or the total all the dipole moments of the individual atoms. The sum of that all together is called as the total dipole moment. And what is meant by polarization, which is written by the capital letter P. This is a vector, and what is polarization vector is actually the dipole moment per unit volume. If you have a total dipole say P, then that dipole moment divided by volume, or you can say that the dipole moment per unit volume is called as the polarization. Okay, so this is about the polarization vector. So it is very important. Now suppose I can say it in another way. Suppose I have n number of molecules per unit volume, n number of molecules per unit volume, then the polarization vector, and suppose P be the dipole moment, each has a dipole moment say P, then the polarization vector capital P is the dipole individual dipole moment multiplied by the number of atoms per unit volume. Okay, so if n was not the number of atoms per unit volume, then you have to divide it by the whole volume. So I can say that if P is the dipole moment of each atom, then if n is the total number of atoms per unit volume, then the total dipole moment, or sorry, polarization vector P can be written as n into P. Okay, so what is dipole moment? Dipole moment is actually, sorry, what is polarization? Polarization is dipole moment per unit volume. And what is dipole moment? Dipole moment is the total sum of the, or dipole moment is basically the sum charge multiplied by the distance between the two charge separately, or the distance between the two separate charges. Okay, so this is all about the introductory topics in the dielectric. So you have learned what dielectric materials are and how they differ from the metals or semiconductors. And then you learned about polar and non-polar molecules and how basically they differ in actually polarization. Okay, then you understood what polarization is. So when you have to say that this charge separation takes place, right? And this charge separation is what is basically known as the polarization. We say that the material has undergone polarization. Okay, so if a dielectric material undergoes polarization, obviously dipoles will be created. Dipole is basically charge separation. So what if I quantify dipole, what is dipole? You can quantify this dipole as in the terms of dipole moment. And what is dipole moment? Dipole moment is the charge multiplied by the distance between the two charges. Okay, so now the dipole moment existing per unit volume within the material can be termed as polarization, termed as the polarization. Okay, so this is all about the introductory topics. Now you go through the individual topics and then we'll have a discussion. Okay, so thank you very much for your patient listening. Thank you.